fourth and final session on AI and other emerging energy management tools available now, which is going to be moderated by Jordan Sager, Associate Director of Facilities Management at UC Santa Barbara. The floor is yours, Jordan.
Thank you. And what a fantastic segue that was, Ben. You really queued us up for this one. So thanks everybody for sticking around. I don't think you'll regret it. This is the AI panel and other energy management tools. But just as in life, AI is inescapable. And so we're going to be talking about how some of our counterparts are using AI-enabled building energy management systems and other predictive forecasting methods informed by AI to make better decisions on energy management and save energy and optimize operations. So with that, let me introduce our panel. First, we've got Colin Moyer with Affiliated Engineers. Colin has extensive experience with district energy systems, serving complex and mission-critical facilities. His work spans utility master planning with detailed lifecycle cost analyses, demand-side assessments and forecasting, and supply-side system design and optimization. He has led central plant design from early concept through construction administration, commissioning, and operator training. Presenting with Colin will be Joe Yonkoski. Joe is the superintendent of UC Davis's central heating and cooling plant. He's responsible for overseeing the assets and staff necessary to operate and maintain the central plant, which is tasked with providing heating and cooling utilities to approximately 100 buildings on campus. Next, we've got Kenny Seeton. Kenny's the Director of Central Plant Operations and Strategic Energy Projects at CSU Dominguez Hills, our only non-UC attendee today. So thank you, Kenny, for taking the time to be here and present and ask great questions. Kenny leads campus scale heating, cooling, and controls to boost reliability while cutting energy use and carbon. A hands-on manager and educator, he specializes in optimizing central plants, integrating BOS and IoT data, and building technician capability and teamwork. His motto is, if better is possible, then good is not enough. Finally, we've got Gabe Sandoval. Gabe is a controls engineer at UCSF Health, presenting for the second time today. Thank you, Gabe, who specializes in HVAC control systems for all types of environments. Through his work commissioning and optimizing building automation systems, he's developed an interest in how AI and emerging tools might complement traditional control strategies. He looks forward to sharing experiences and learning from colleagues about practical applications of those technologies. So with that, I will turn it over to either Colin or Joe, whomever will be presenting their screen for us.
All right. Yeah, I'll go ahead and present the screen. Thanks, Jordan. Okay. Good to see a heat pump diagram on the screen, if I've got the right one. So we'll just dive right into it. We're talking a little bit more about, in this brief session here, an emerging technology in the heat pump market. And just to put everyone on the same page with what a heat pump is, there are many types. In bold, we're going to be talking about a liquid heat source, a liquid heat sink, a vapor compression cycle that is electrically driven. However, there are quite a few different variations of heat pumps, as you can see listed out on the slide. But basically, they are all something that use work to move heat from a lower temperature to a higher temperature. So a chiller is a heat pump. It is called a chiller because it makes chilled water and it wastes the heat. And we're looking here at a simple diagram of a separate heating and cooling system. And then we build on this diagram with some heat pumps. So, for example, we can turn a chiller into a heat recovery chiller. They're both still heat pumps, but we can create here a combined heating and cooling system. We call it a heat recovery chiller because of the waste heat in the cooling system. Instead of it all being rejected, some of that is recovered, and that can be used to displace the amount of high-grade heat that we need in our heating system, which would traditionally have come from fossil sources. Building on that further, there are a lot of different types of heat pumps that can be deployed, and we actually presented at this workshop a couple of years ago, I believe, with kind of a market update on different heat pump technologies, and that market continues to evolve. And today we're going to talk about some of those emerging technologies that UC Davis has been very carefully considering for the TES plant. And at the end here, Joe's going to take you through what was selected moving forward for the UC Davis campus. This just shows how there's a vast web of different heat resources that can all be mingled together when you use heat pumps. We're not going to go through all the bullets here, but these are all the different types of technologies that we look at in decarbonizing energy systems, and the heat pumps are at the center of it all. They're deployed to move heat from cold batteries to hot batteries, to recover heat, to pump heat from low temperature reservoirs. But basically, everything here is designed to displace the amount of fossil fuel combustion for environmental benefits and reduction of global warming. Looking at the heat pump a little bit more specifically, as far as how it uses energy to move that heat from low temperature to high temperature. Looking at the amount of work that needs to be done is going to change at different temperatures. So if you have what we call a low temperature heat pump that could be delivering about 170-degree hot water while it's sourcing heat from something similar to chilled water temperatures, you're going to have a COPH there of around 3. It's going to depend on what type of compressors you have and exactly how the machine is designed. But you're basically going to generate 100 million BTUs per hour of heating by recovering 67 million BTUs per hour of cold thermal energy and using 33 units of work. So the work and the cold are combined into the hot. If you were to deliver at a higher temperature, though, it's going to take more work to deliver the same amount of heat. So you're putting in more work, you're recovering less of your from your low temperature reservoir, but you're getting the same amount of heat out. So in this case, you're using 50 units of work. As you go up into steam heat pumps, you get even less efficient. You're looking at, in this case, a COPH of about 1.5. So all to do the same thing here, where we're looking at making 100 million BTUs per hour of heat. If we need to make that at about 350 degrees, we're going to need 67 of those units to come from work, and we only recover 33. And lastly, with an electrode boiler or any kind of electric resistance heater, of course, you're going to need 100% or possibly a little bit more than 100% of that input energy is going to be required to make 100 million BTU per hour output. So this is just some background in terms of why UC Davis already embarked on a campus-wide steam to hot water conversion. That 350-degree steam system is in the process of being converted to a 170-degree low-temperature hot water system, possibly could operate even a little bit lower than that. And so that's going to improve the efficiency. The amount of work required is going to be cut in half from 67 to 33 for the heat pump system. And so recently, the UC Davis has been looking at proposals from different design build providers on the low temperature heat pump system. And it came down to a very close analysis of 3 different types of machines. We've got at the left depicted a multi-stage electric driven water-to-water heat pump. In the middle, a compound unit, and on the right, a cascade system. So the multi-stage unit is one of the latest emerging technologies on the market, and it was recently released in the equipment that's about 23 to 27 million BTUs per hour heating capacity. It uses a 3-stage compressor. So that's a single semi-hermetic electrically driven compressor, but it has 3 impellers in it. And because it's doing a lot of lift from 39, 40 degree chilled water, all the way up to its capability of 170 degree hot water. So this is a very intriguing heat recovery unit, but the con is that it's currently only available on the market in larger sizes. 23 million BTUs per hour is kind of the smallest size. Also, in order to purpose the evaporator for beneficial cooling, you like if you don't need all the heating, you have to dump the hot water. You have to waste some hot water if you want to get beneficial cooling off of a machine like this. We've been pushing manufacturers to develop an option that has a lower temperature heat rejection condenser bundle or possibly a separate shell, but that's not readily available on the market. So if you want to purpose this as a chiller only, you end up with pretty inefficient cooling because you have to make hot water and then use heat exchangers. The compound machine we were looking at for a number of years for UC Davis. That consists of two separate compressors that are essentially in series, but their refrigerant flow is balanced out by an intercooler. So this is like the traditional York CYK. Again, there are some downsides. The larger legacy CYK that can do 170 degrees is not readily available with heat rejection equipment. York did release a smaller CYK that is only 400 tons in size, and that one can do low temperature rejection. But the market just isn't quite there yet, unfortunately. The way that there are two compressors in series, there's actually a really good opportunity to divert the discharge from the low pressure compressor into a heat rejection bundle. So this is something that's still emerging on the market to follow in terms of deploying these larger water-to-water units. Because if we could get equipment that could do heating duty in the winter, but also do efficient cooling in the summer, all the equipment can kind of be consolidated, and it'll help with payback for decarbonization projects. And lastly, we have a Cascade, and this has been around for quite a while, although there are some newer products on the market with the latest refrigerants that can do the high side of a Cascade system. In a Cascade system, you basically got a conventional chiller on the low side, and you're heating water a little bit warmer than typical tower water, and then you're using that as a source to heat it further in another water-to-water heat pump. Downside of this is that you do have some parasitic lift because you're condensing on water tubes, and then you're pumping that around. You've got a differential temperature on that intermediate loop, and you've got another approach on the tubes of the other evaporator. So you're doing a lot more overall lift than you actually needed to do to get from 39 to 170. But the upside of this is that you have a lot of flexibility because you do have now an intermediate fluid loop, and you have regular chillers here, and you can mix and match operations. So if you want to make more chilled water than the relative amount of hot water that would be produced, you can connect towers or other heat rejection equipment into the intermediate loop. And then you can do pretty efficient cooling operation for that excess cooling load that you don't need to recover in the spring and summer months. So put those two different options together on this diagram. The compound arrangement or the multi-stage arrangement on the left, shown as if we could get a double bundle condenser. Alternatively, if the manufacturers aren't offering that, you've got to have a hot water to tower water heat rejection system, which is an additional cost. Versus on the other side, a representation of a cascade arrangement at the TES plant. So Joe's going to talk about how the proposals were analyzed against each other and what UC Davis is moving forward with.
Thanks, Colin. Yeah, so I want to talk a little bit about the criteria that the UC Davis panel considered. There were a lot, but I just want to touch on a few here. So although this is ultimately a heating project, because it's heat recovery, it does affect the cooling system, and it can affect it pretty significantly depending on what type of equipment is selected. So one of those factors is the double bundle that Colin mentioned. the manufacturers weren't willing to commit to that. So those strategies that employed or that could have employed that were kind of not on the table anymore. That's because the efficiency and the cost to get rid of excess heat in the summer for those options would just be pretty bad. So we ended up going with the Cascade option. And I'll show that on the next page in a second. Another important factor is the cooling capacity. So also some of those newer machines weren't really a in-kind replacement of some of our aging chillers, whereas the Cascade option did allow that. So it was another factor pointing us in that direction. We want something operationally simple. We don't want a science experiment. We need to cool the campus, heat the campus. So we were a little leery of kind of being first of a kind on some of this equipment. And we need the heat pump to be able to modulate up and down, meeting load as needed. And some of those other options mentioned couldn't do that quite as well as a Cascade system. Another consideration was total footprint. So we want to maximize the space we have now. So in that respect, Cascade, you need two separate machines. So you'll need there, it's not as well, but at the end of the day, it comes down to cost. And we had a fixed project budget, and we were trying to just get the most capacity and new equipment and equipment renewal that we could with that budget. Next slide, Colin. So this is kind of a schematic of kind of the existing and new plant. So you can see the chillers that are kind of turquoise color, those are new. And then the brownish ones are already existing. There's a existing chill water storage tank, which David talked about earlier, existing cooling towers, and then there will be high side heat pumps, which is part of that Cascade loop in a new separate building, and then hot water pumps also in that building. We're also putting in a hot water storage tank, which is number 5 on the diagram. And there's also needs to be a small intermediate tank, which is number 4 there. And that's to provide enough time for the heating and cooling equipment to adjust when loads are changing. Next slide. This is kind of a simple flow diagram of what that equipment will look like. So again, existing train chillers, and then it says one new 4,000-ton chiller. We actually asked them to split that into 2,000 tons. And that was to help with redundancy and reliability. We didn't want a single point of failure for quite a large chunk of our heating or cooling, I'm sorry. We're getting 2 high side heat pumps in this phase, which will interface with the tank and the buildings. Next slide. So comparing the Cascade option with the multi-stage, these are some of the numbers the vendors put in front of us. With Cascade, we'd be able to renew 4,000 tons of cooling, that was our goal. With the multi-stage, because of the size of machines, we just couldn't quite get there, and because of cost. The heat dump, when you have excess heat available in summer, that was a big factor. The Cascade can use cooling towers at a much lower energy penalty. The multi-stage, because it doesn't have that double bundle, you're using heat exchangers, putting tower water through heat exchangers, or using very large shell and tube heat exchangers. It just wasn't really palatable. Both can make hot water, but the Cascade option can make a little bit hotter water. We don't expect to need to operate at 180. We think we'll be able to operate at 160. It's still nice to have the flexibility. And then the maximum heat output that we could afford with these 2 different types was higher with the Cascade. And early on, the utilization will be lower because only half the campus is converted to hot water. But over time, it will be more beneficial, and to get that in sooner, saves costs down the road. So we end up selecting the Cascade option. I believe that's our last slide. So yeah, we're happy to take any questions at the end or now.
Thanks, guys. Let's hold questions to the end, and let's just march on through to Kenny, who I believe is next.
All right. All right, so central plant optimization and electrification. So a little AI, little heat pump. So the campus currently has 3 1,000-ton York chillers, water cooled. We have 4 Tower Tech cooling towers. And then we're a JCI campus. So how did I get here first? The goals that I had, right? My goal was always to move the needle with whatever resources I could get my hands on. And my new goal now is to get rid of scope 1 and 2 emissions before I retire. Why AI? Why heat pumps? When I learned about the guy that was doing the Facile.ai, he was super smart and had experience with every control system that I could think of. And I like to be friends with really smart people because that's how we all get better. I didn't see any downside of AI. To me, it's just faster computers, which is right where we've come from, right? The computers keep getting faster, our controls get better. Facile AI is the next level of what I'm already doing, right? It can do it faster. The heat pumps was to burn less gas. We're all talking about decarbonization. And when we designed the heat pumps, it couldn't just make hot water, it had to also feed into the energy loop. And when I say heat pumps, I mean big heat pumps. We got rid of 95% of our gas for heating the campus. The campus from the central plant feeds about 1.5 million square feet for the heating and cooling. We didn't get rid of the condensate boilers. We kept them for backup so that if it gets really cold, we can turn them on in a pinch. The real data, so when the heat pumps are running, the boilers aren't. The graphs that we see here, the red is gas usage and the blue is chiller electricity. And so in the wintertime, when the heat pumps are running really, really hard, the chiller plant is slowing down also, which was a really huge, bigger benefit than I thought we would see. Where we got there, so we were just doing chillers and boilers forever. We tried out a different so-called AI vendor, and we tried it for about 6 months. It worked, but not to the extent that we needed it to. It wasn't consistent enough, didn't take into account all the time. Then we tried out Facile. It ended up giving us really stable, consistent chiller savings, and we can see those in a minute. And then we added the heat pumps. So it kind of skewed some of the savings numbers, right? Because you can't do all these different things and it's hard to model, but got some data that will show you where that goes. The results of all that and all the other energy efficiency stuff is that we've reduced our greenhouse gas by 62% from our 1990 level. If we go to 2018, then it's really like 71%, but at what point do you decide that you're reducing? And that's with adding 300,000 square feet, and we're still adding buildings. In 2024, this is our efficiency at the bottom, right? This efficiency level is the total plant though. I don't really worry about, you know, the actual chiller efficiency because it's about the total cost of making chill water. You can see that ASHRAE is telling us that, you know, at the chiller, our best is 0.45. And we were averaging about 0.45. Before that, we were 0.86, 0.7. We came up with these numbers by taking a year's worth of data, 15-minute trend data, you know, throwing out the high, throwing out the low, and comparing them together. you can see the graph of where we used to be on our efficiency. We used to run the plant like a lot of people, 5 degrees above wet bulb. What the AI is doing is it's adjusting our condensing water set point. Instead of it being just a static 5 degrees, 7 degrees, 75 degrees, it's dynamically adjusting it every 5 minutes. What we're finding is that it's not always better to burn more fan horsepower to save compressor horsepower, but there's a point where the two mix and you got to find out the point of diminishing returns. So here was a snapshot we did October 21st, 2025. This is a central plant summary page. At this time, the total plant was running at 0.48 kW per ton, and the chiller was actually running at 0.24. We were doing 620 tons with a 1,000-ton chiller, and our load was only 27%. We were doing 50 degrees. There's a lot of things that come into play here, right? You know, what's your temperature that you're running? What's the outside air? What's the wet bulb? What are all these things? All those things we're using and we're inputting it into the AI, and it's changing the condensing water temperature set point. How are we doing it so that we feel safe, right? Because that's a big thing, right? People are worried that the AI is going to take over. It's going to break your equipment. It's going to break something. What's going on? So we wrote a real simple program. We call this input the heartbeat. If it doesn't see a signal from the AI every 5 minutes, then this statement goes to a 0 and we end up false. If this is false, we come back to our old settings, 5 degrees above wet bulb. We put a kill switch in so that if our operator sees something that makes him nervous, or AI loses its mind, right? We can kill it and we go right back to our old programming. Somebody had said this in the beginning, right? Let's run this outside of our control system, right? So that we're not taking over. We always have our fallback. We can put limits in there, right? What's the highest temperature you want to run? What's the lowest temperature you want to run? So we build the guardrails. We build guardrails into our own programming. It's no different than building them into the AI program, right? If there are hard limits that you need to pay attention to, then you write them into the program and you're good. But you also write them into your own stuff if you have to. What does it look like? Here's kind of a behind the scenes, one of the screens we don't ever see, but we pulled this out, right? And so every 5 minutes, we're making a change. Condensing water temperature set point 67.88. 5 minutes later, it's 67.67. So it's always making those little micro adjustments in order to run at the optimal. Its programming is what's the best kW per ton, and it's going to try and hit that. Takeaways. AI has no downside. It's just a faster computer in a sense, right? We all do sequence of operations, right? Maybe you're looking at, these factors and you're writing this complicated thing, or maybe it's really simple, 5 degrees above wet bulb. Or maybe it's written in another server and it's saying, hey, I want you to look at all these 6 things and I want you to tell me when it's running the best, and let's make a little adjustment, see if we can make it better. For campuses that don't have really strong facilities control specialists, right, that you rely completely on your proprietary control company, right, AI can help us because they can write a program that can just go in there and make your stuff better. And if it doesn't work, you go back to your old inefficient way of running things. Facile AI has 0 implementation costs. So to me, there was no risk, right? If it didn't work, you don't pay for it. There's no hardware. There's a gateway that talks to your system and does everything. And then plan for your savings if you're going to go down this route, because I guarantee you, you're going to get huge savings if you use the right person. I didn't, and so I'm getting these huge savings, and the campus is, once in a while I get a pat on the back. Hey, thanks, Kenergy, that's good. And we keep going. So we use SkySpark. Every one of the points is brought into SkySpark. This is just a utility thing that we're looking at, right? 2020 was COVID. Campus went down, then it started growing. The one thing that we found was when we first did the heat pump, I didn't factor in the time that the seal was running because the energy use went down so much. And when I looked at it that way, there was no ROI, right? The heat pumps are never going to pay for themselves. Yes, I got rid of 95% of my gas, but my electric went up a lot. And so it cost me more. That was, I ran that in the beginning. Well, now I've had it running for almost 2 years. And now when I run the numbers, I find out that the total cost to run the central plant is actually cheaper than it was before. And that's with the heat pumps. And so by decarbonizing and electrifying, I actually brought my electric bill down because I partnered it with the AI. 21 30-ton heat pumps. If it was just the heat pumps, it was people and planet, right? We reduced the greenhouse gas. We did the right thing. But we needed to bring the AI into it so we could have the people, planet, and profit. And thanks a lot. Questions later. Thank you.
Thanks, Kenny. That was great. Yeah, we'll do questions at the end. Gabe, give you a second to go ahead and set up and share your screen.
Are you seeing my screen?
Sure do.
Should I be in? I'm good.
Yep, go for it.
Okay. Thanks. Yeah. So I'll hopefully I'll keep this interesting and quick for everybody. Yeah. So I'm just gonna just touch a little bit on AI in regards to building automation. Again, that's kind of my area of focus. Right away, I'm gonna say I'm not an AI expert. So I was tasked to talk about this, but again, I tell everybody I don't consider myself an AI expert. I was an early user, or an early implementing the technology. I constantly told Anna, I said, we need to spend more time using this as a tool. There's a lot of good benefits. She probably noticed my emails got much better. So yeah, I've been actively using it for pretty much since its inception, and trying to stay, continue to research better ways to use it. I consider myself more of a technologist, right? I just love using different technologies, researching, trying to find better ways to run our buildings, and particularly with building automation systems. What about AI? So how can AI help with building automation, building technologies? Specifically, I'm when I talk about AI in this particular case, I'm talking about AI. One, using it as an assistant, and primarily an LLM model. And I think it's good to kind of understand the different models, what different models do, and what their focus is on. The first thing that I started looking at it is for sequence of operation review. And this, it is interesting because, again, in LLMs, if you understand those models, it's a language model. It's built around understanding language. When we focus in on HVAC, and how it operates, it deals with thermal fluid dynamics, right? Space relationships. You have to be able to understand 3D, airflow within a room, heat flow within, rooms, and things like that. So inherently, LLMs are not really built for understanding HVAC. And I think that's a key thing to understand. Like what Kenny was reviewing, that AI, I probably guarantee, is not an LLM model. It's more like a machine learning model. It could, have a better understanding of like multivariate time series, space relationship, that type of AI. And those AIs have been working for quite a few years now, and they did work really well. When paired with like an LLM, that's when it becomes much more, dynamic. So when I started looking at potentially using it as a sequence of operation, I was curious to see how would an LLM do on a sequence of operation for figuring out like a plant control. So I had a project here we did, I think Anna highlighted earlier. It was an all-electric building plan, a very complicated plan. We were having a lot of issues with it in the beginning. The sequence of operation that originally was written and was deployed was not working well. And so I had been spending a lot of hours kind of going through and trying to figure out what's going on. So I ran it through, and I was really curious of how well it understood the operation of the plant, particularly, understanding the significance of heat dominant mode, cool dominant mode, and in relation to all electric plants and heat pump chillers, and you know the when buildings need to, do chillers switch modes? Is it better to switch them? Is it better to keep it in one mode? So it gave back some really good feedback. So what happened is, as I saw that, I began to like think that, wow, this is actually pretty decent in understanding. It wasn't perfect, but it's pretty decent. In my day-to-day job, I have to support not just existing buildings, but a new construction. And we have, aside from those ones that we just commissioned, we have 2 more projects, big projects that we're doing that are all electric, both hospitals, and each plan is different. And so I get asked to review the sequence of operations, and I don't have a lot of time to go through and try to understand completely the sequence before I give my comments back. So after I did that project, then we had this next. This is our HDH project that I'm referring to now, the Parnassus Hospital, and particularly the LLM. If you're curious, the LLM I like to use is Claude. It's one of my favorites that I prefer to use. So I was like, okay, they wanted me to give feedback on the sequence. It was a very rough draft, and I said, well, let me see what I could do with this. So Claude allows you to do something like, if you kind of know AI a little bit, you might know what a RAG is. And so it allows you to set up kind of a mini RAG. They call it a project, where you can upload files, and it allows you to be able to focus in your questions, particularly on the files that you upload. So I did that. I uploaded the sequence of operation, the drawings, any other information that was relevant, the chiller manual, because I needed to understand how the chiller ran. And so you can kind of see here the sequence of operation that I brought in. It's just part of it. It was a very rough draft, and they told me that it needed a lot of work. So then after I did that, and it spits out, pretty good information. You can kind of just, again, it's a lot to distill here, a lot to look through. But it broke it down really well. And it's amazing how much it does understand being an LLM model to understand, how a plant operates. What was great about it, again, is it helped reduce my time that it took me to help understand key points of this sequence of operation. I didn't add it here, but later I had to generate a bunch of questions, and then I went through and threw out most of those questions and dialed it down to the questions I want. Finally, I was able to submit that to the team. The other thing I did is I actually had to rewrite the sequence to simplify it. And I submitted that back to the project team, and they were impressed by what it had produced, because it really cleared up a lot of the things that weren't very clear with the project. So yeah, again, interesting that it could understand pretty well, not perfect, but it does a really good job. And I think there's a lot of potential for this. I had to do something opposite, where I had it on the previous project. I was curious to see how well it did in just rewriting the sequence and then generating like alarm list and things like that. And it did a really good job, like coming up with a list of alarms. But again, not perfect, but very good. I think it helped reduce a lot of labor time, like it did with a lot of things. So again, interesting way I think to deploy it. I'm curious to see if others have done this as well. Another area of focus that I've kind of done some research on is control system programming, and couple areas I think that it really can, or one area that I think it can help, is just being able to understand, I guess be able to use it kind of as a knowledge base. We had one building that had a new control system that I wasn't familiar with. So I uploaded their programming guide, and then I just started going through and just asking it questions, because if you're kind of familiar with control systems, each one, they have different terms, and I mean, there's a lot of things that that are very different between the different programming languages and things like that. And again, as a user, somebody who supports a facility, I have about 4 or 5 different programming systems that I have to support, and I can't always remember specifically with each one as I go from one to one. So I needed something to help me to kind of refresh. So like in this particular case, I asked it questions about the PID, and there were specific terms that this programming system uses that I couldn't remember what they were for. So I would just go through and just ask a question like, tell me what this is for, and then it automatically spits out the answer. I shared this back with the control company, and they wind up setting up a whole large knowledge base within their whole unit that they now depend on. So any technician programmer has questions, they have a way they can easily go to and grab or find out get answers to any type of question. So again, recommend it, if you're not using it for this yet, I mean, I think it's a really great application for AI. It does really well with this. Another area of programming that I was kind of curious about is vibe coding, and I heard somebody use that term earlier. If you don't know what that means, it's just using, if you're not a coder on your own, it just allows you to do coding for you. I was curious again, can AI help with vibe coding, building automation, right? I think I kind of follow a lot of forums and LinkedIn, I hear a lot of people talking about it, the potential. I find that it is very challenging, I think, because one of the things that has a challenge is that BMS programming tools are proprietary. Things that are more open, that like a good example is Python. Like Claude has a something that you use called Claude Code. And so you can go in and say, generate this in Python, and then it allows you to automatically run it, debug it, test it out. And you can kind of go through the process, and then eventually it spits it out, and it's a working code that you can deploy. Same thing like with HTML, you can have it write out HTML code, and it's ready. You can test it, look at it, and you can deploy it. If I tell it to write programming code for Distep in GFX code, or write it in Tridium, or write it in some of these other ones, it can do that. Those are proprietary programming languages. It can, again, it can serve as a knowledge base, but there isn't any tools that allow you to be able to generate that code out and make it usable. And so I've talked to some of the control manufacturers about the idea of setting this up. The one I think that's supposed to be coming out, I heard, is SkySpark, which is a great thing. So I know we have a lot of SkySpark users. I heard 4.0. They built that feature within it, so you can just use a prompt and say, write an analytic that does this, and it'll automatically write the Axon code. So I think that's very cool, and I'm looking forward to seeing that. But again, I think there's some work to be done there. The other challenge with certain programming codes is they're graphical block based. LLMs again are language based. They're not visual based. And so they do have challenges generating things like this unless you specifically build it out and train it after a while on it. So I think that's always going to be, or at least in the immediate future, a roadblock to this. So I see the programming languages that are more line code, like Delta Controls uses line code, and I think Siemens, has some that are line code. I think they're actually going to be much easier to eventually start vibe coding with, rather than some of the other ones. So anyway, just something to keep in mind. One other area that this is the one I'm really interested in is AI agents. If you don't know what an agent is, I encourage you to spend time looking at it. As what an AI agent is essentially you can assign it to do work for you. So it really is where the development is happening with a lot of these AI companies, is developing these customized agents for different aspects of what people might use it in business. I've already seen this like with building automation, where companies are offering to set up agents for building automation, and if you think about the potential is pretty interesting. I was kind of like just thinking about and doing research on some of these potentials of what an agent can do for a building. Like again, like here in breaking down complex engineering tasks, interfacing with the building automation system, being able to look at your front end and generate trends for you automatically. You know, again, looking at projects, kind of what I mentioned earlier, automated commissioning agent, you know, being able to just tell an agent to go through and commission your system. Even doing integration work, like if you wanted to have integrate a building automation system into a SkySpark system, right? There's potential you can set up an agent to do that. We talked about ongoing commissioning. Any of these things that agents, you know, could potentially be able to do. There could be different levels. You know, if you think about what an agent can do, you could just have it like read the reports and generate data. Modify set points, that might be a level. That's something that Kenny, you know, they're starting to do with the system that they have there. Implement control logic changes. I mean, that could be a potential. And then you may have one that's a fully autonomous system. And imagine what that might look like. I was talking to Anna about this the other day, and you know, you can imagine a situation where a technician or engineer wants to override a point, and the agent, you know, maybe puts up a red flag and says, you know, don't do this. If you do this, you're gonna cause this to happen, or this might be a better thing that you can look at doing. You know, there's a lot of potential that could happen with that. Having said all that, is this a possibility though? Is this something that that should be done? Well, I think there are some challenges that have to be considered, because again, these things are being offered, and I think if you haven't been shown it yet, you will be very soon. But right now, these agents live on the cloud. There are no agents that are built to do this to this level that are on-prem on the edge. So the cybersecurity issue is huge. That attack vector, you can imagine if somebody was able to get into the prompt and change that, whatever agent's running on your building, I mean, it could cause serious issues. So I've already don't use cloud for a lot of reasons. I've been shown cloud front ends, and I just haven't found one that I feel secure enough to want to use. But then thinking about what, you know, having an agent on the cloud run on your system, I think that the danger is extreme. So you know, as of right now, I don't think it's ever something that I would do. Um, I just think there's too many things to consider. And again, one of the things that again Kenny talked to us a little bit about, but you know, what is some of the liability involved? What if it makes a change that causes the building to shut down? Who's going to be responsible for it? So I think there's a lot to be worked out if this is ever to be a thing to use. I do think though that the future will be some type of edge AI agent. It's not something that's fully developed yet. I think it would involve some type of, you know, models that run like similar to, again, what Kenny, you know, is using there with an overlay of like an LLM or something like that. Um, I think it will be there soon. I think we will see it. It's not there yet, but that's something that I'm looking out for. And again, as mentioned, you know, it had to have some strict boundaries for critical spaces as well. Just thinking about the future though, of if what this might, you know, if they're able to develop it, and I think they will. One of the things I'd recommend that we're doing now is store your BMS trend indefinitely. The one thing, if anything, you learn about AI is you have to have data. Data is how these things are built. So I would recommend you know, now is the time, if you're not doing it, store your data, your trend data indefinitely. I think it is a valuable source. I was on a panel last week for the local ASHRAE, and I told everybody there I view data as a commodity. It's a value now. It's going to be something that's useful for training AI models. So I would highly recommend that you store it, standardize on some type of semantic data model, whatever one you might be familiar with or like to use. And then the one thing I would like to throw out there too, and again, I know we have a lot of UC here, is I really feel that there would be a huge value to somehow create a stored data of all the UCs. I think, you know, if you think about again how important data is for AI, I feel like there's a huge value that we should start planning for this. I think it is capable. You could cost effectively do this now. You know, I think there's other, you know, reasons to do this for, you know, research. But I think in the future, if, you know, if this AI, again, my vision is an agent on the edge, the way to train it is going to be data. So if we all have data to use, I think it's all going to benefit us. So, you know, I'd love to see somehow UC look at implementing this or finding a way to do this somehow. And that is it. That's all I have.
Thanks, Gabe, and thanks to all of our presenters. Something that you said there at the end, Gabe, about shared data repository kind of caught my attention. It is something that UC has looked at in the past, and we've looked at SkySpark as a platform to essentially dump, multiple buildings from all across the system into as far as trend data goes. But I guess when you're talking about an AI application on the edge of a BMS, what does that mean in implementation terms, and what do we need to go tell our cybersecurity folks on campus when we're trying to bolt something like that on? Is it part of Kenny's JCI package or Joe's Siemens offering, or is it something separate and in additional to?
Yeah, I mean, well, I think maybe Kenny might be better one to answer this because I'm sure he might have had to get it approved somehow. But yeah, I think it's like any technology, right? You go through the process of vetting it. Often we submit our new technology that we want to use to IT and let them kind of do their due diligence. But yeah, I think, like I mentioned, liability, compliance are huge factors to think of. Because if we're at some point going to allow some autonomous system to take control, the potential for disaster, we can all think of the things that could happen, could be tremendous. So I think it's something that would have to be worked through.
Kenny, can you describe the process there? Did you get any pushback on the Facil.ai implementation, or?
No, because I ran it on a desktop computer.
Okay.
Right. So we were kind of the pilot site, working through all the different issues and problems. So we just kept it running, on a secure desktop that could access the and then since that time, he's built it out to where it runs in the cloud, but for me it's running on a desktop. So I haven't gone down the IT path yet. But Channel Islands has, right? And so there is a way because they're doing it over there.
Okay, thanks. Mark asks, I think this is for Gabe, the name of the AI tool. Yeah, that was Claude, correct? Okay. Have any of your campuses sort of institutionalized a particular AI platform or tried to push anything out in a more formal way, or is it still kind of a free-for-all?
I mean, we just found out that they're doing an enterprise ChatGPT. They did have an in-house one that they're working with ChatGPT called Versa, but I think now they're going to push this out for everyone to be able to use.
Gotcha.
Yeah, the CSU is using the enterprise ChatGPT, but there's a lot of things that if you're a private commercial enterprise user, you could do. Like we can't do agents, right? So there's things that they've locked out, kept us locked out of.
Right.
Because of people like me that are going to push it. I'm kidding. I would never do that.
So we've got about 6 minutes before we need to wrap up the final panel. So I want to make sure that everybody has a chance to ask any questions that they've got out there.
Just real quickly, Jordan, as we're waiting, but you did mention about like systems to use if we did like a master database, but there's a new one called Nobant.io. It's actually one of the same creators as SkySpark. And it's a fairly cost-effective way to store data that supports tag-based data as well. So I've talked to them. He's been around a little bit, but it seems like a very viable solution.
And I just want to follow up, Gabe, with your suggestion of a system-wide data repository. It's interesting. We can maybe follow up on that more, but have you gotten any feedback from your IT folks on what something would take or what it would take to engage with AI, like you said, it has to be operating on the edge, but have you even introduced that idea to your IT? And I'm just curious what kind of feedback people have gotten on that concept.
I haven't. No, not with an agent. No. I just don't feel it's ready for what the application that I was talking about. So yeah, no, I haven't.
And Kenny, you said Channel Islands has gone one step further. What does that look like?
I think somebody from Facilities here, I think they're doing 31 or 32% increase in efficiency at their chiller right now. And it's only been running for about a month or so. So it's substantial.
Okay.
And I think the other thing that we didn't, it got talked about a little bit by Anna and Gabe. The other thing, like we're using it for one thing right now, right? We're using it to control the set point, but and we have, I've got a very advanced facilities control team here that, I stole from JCI and stuff. So we can do things, but the average plant can't, right? You're handcuffed to the vendor that you have to, pay a whole bunch of money to make these changes. And I think that's one of the things that the AI is going to help us with, right? Because now you can have these modules like smart stop or start stop at the building level, right? And economizer control and these ASHRAE 36, right? That we can go in there, and as long as you have a working, in my mind, I would make sure I had a working system to start, because then, if the AI doesn't work right, then you just run the way you've always run, right? That's kind of the beauty of it, as opposed to, well, ASHRAE 36, right? I've gone on the record, I'm not a big fan, but I was a very early adopter, and they programmed 2 of my buildings for it, and it's so complicated that we have to redo the entire building to take it out, right? Because of all the different signals that it has for economizers and for this and for that. If you had done that with an AI program, you just turn it off, right? And then, okay, what are the tweaks I want to make? I mean, I think Gabe was talking about earlier, right? It's like we can experiment with these things. It's a hospital, right? We can't afford for it to be down. But if you rewrite your sequence of operation in your building automation system, it's a lot more complicated to go back to something. So there's going to be benefits there.
Yeah, and that's exactly the point. I think you're understanding exactly what I was looking at, is that I think, right now, like I said, I think living to that degree where it's not overriding, setting set points and all that, making autonomous decisions I don't think it's ready there. But in lieu of that, the preparation for us is what I was showing, which is, let's get it out of the controllers, let's bring it up a level, and let's maybe use Skyspark right now, and let's do some advanced logic for dealing with resets and things like that. But the future, I think, eventually is you should be able to just pull that out and put this this AI in its place. And I was noticing John, like, I don't know John Carpenter, but I saw it feels like a non-stop. I mean, yeah, I would say, yeah, I think right now people, there is a lot to worry about AI because there's so many questions around what it can do. I think over the next few years, we'll see a lot of that worked out. I think you're going to start seeing more, applications for edge AI. I think, like Chris was mentioning about it, you can run these LLMs now. You can download them and run them on a computer and play with them. They're it's that level right now. But I think eventually we're going to get there, and people are going to feel more comfortable with AI. IT teams are going to feel more comfortable with it. And with proper safeguards, I think it's going to prove to be a very valuable tool.
On that note, thank you all again. I think that's all the time we've got for the final session. So I'll turn it back over to Maria, I believe.
Yep. Thank you, Jordan, for keeping the final session on track. And to the speakers, thank you all for participating in this very interesting and much needed session on AI and emerging tools.